Pretty cool. Let's go ahead and welcome our panelists to the stage now. Come on.
Hello, everyone. My name is Vijay. I run this group called Outshift inside of Cisco. It's the internal incubation engine for Cisco. And as part of that charter, I also have Cisco Research, Cisco DevNet, which is the developer relations organization, and open source. And the charter of Outshift is to build products that are adjacent to Cisco's core markets. Adjacencies could happen in terms of personas. So we always talk to network engineering persona or SecOps or AppOps, WebEx and collaboration. So are there products that we can build that are adjacent to those spaces? As well as can we build products which are a bit further out and are a little riskier when it comes to technology or market? And clearly the topic of today, quantum, is in that space, which is these are technologies that are a little bit further out, but they're happening faster than one can imagine. So with that, I'd like to introduce the panelists here. So let's start with Anthony. Go ahead and introduce yourself.
My name is Anthony Greco. I have the pleasure of leading the Security and Trust Organization. Our mission is to help protect Cisco and work with all the products that we produce to help make sure that they're ready for the future from a security perspective. And in particular, we'll be talking a little bit about post-quantum crypto and how we protect information in the age of quantum computers.
Bill?
Hi, everybody. I'm Bill Gartner. I have responsibility for our optical systems business, which are the systems that are used to carry traffic over fiber optic networks that are traversing a city or a country or even subsea. And I have responsibility for our optics business as well, which are the optics that are used inside a data center or central office.
Ramana?
Yeah, so my name is Ramana Kumpella. I lead Cisco Research, and I'm a Cisco Fellow as well. And my team actually conducts research in emerging technologies of strategic interest to Cisco, AI, networking, cybersecurity, what have you, and the topic du jour, which is quantum. So really excited to be here. And
so we've got everything from research to product to whether we can deploy it securely in the organization. So we're going to have a fun conversation here. But what I wanted to start with is, in general, show of hands, how many folks out here think that quantum computing will be a reality in the next 5 years? Wow, that's like optimistic crowd. I was like 70%. So how about 5 to 10 years? I think that's the remaining 30. And so 10 plus? We need to convince the three of you. So let's spend some time. But there is some real artifact just behind this stage, or in fact in front of it. So we can walk over there and there are people who can explain what we're building. But let's get to that. So I think I'm an optimist. A bunch of folks here are optimists. But we're also realists in figuring out what we can do today and what we need to solve for making that 5 to 10 year roadmap a reality. And you hear a bunch of news all the time, just like AGI. I mean, I think this show has been all about agentic and AI. And people talk about when will AGI or artificial general intelligence come to the scene? And the real question is, does it matter? Because yes, there is some definition of AGI. People can't even seem to agree on it. That'll happen sometime in the future. But we have pragmatic use cases for AI, for generative AI, for agents, even today. I think of quantum in the same way, which is there might be a time in the future where pragmatic scale-out quantum computing might happen, but there are real-world use cases that are being discussed today, that we are trialing today, that we should talk about, and we are all excited about. And the other thing I want to just phrase up front is, whereas everyone else talks about quantum computing and compute nodes, these are the servers that can actually do quantum computing and run those algorithms. We are in the business of building the secure networks that connect all of these quantum compute nodes together to form what is known as distributed quantum computing. So we are in the quantum networking and quantum security space, and that's what we are primarily going to focus on in this conversation. So with that, Ramana, I'm going to come to you. We just announced the Santa Monica lab. It's at the nexus of a whole bunch of research that's happening in Southern California. There's Caltech, there's UCLA, there's UC Santa Barbara, and there's labs from Amazon, Microsoft, Google, and Cisco in Southern California. So what is it that we're doing inside the Santa Monica lab?
So, Cisco's quantum research program is the goal of it is basically to build a world-class, quantum network of the future. And the Santa Monica lab, the quantum lab, is basically where we have our small but mighty quantum team led by Reza, who's actually in the audience, and they conduct research in developing the next generation of quantum network hardware, software, switches, entanglement sources, all kinds of stuff. And you can see some prototypes out there in the Outshift booth, which are a result of all the hard work that the team has put in over the past several years. And this is just the start. I mean, there's a tremendous amount of excitement around quantum networking. And to touch upon what Vijay was mentioning, to truly transform quantum computing and bring and pull in the timeline of practical quantum computing significantly. And quantum network is a big part of it. And this lab is all about basically doing the experimentation, research prototypes, all that stuff.
So we talk about quantum computing and the practicality of it. And if you know that quantum computers actually work on quantum bits or qubits, which are different than regular classical bits. So can you give a quick 30-second explanation of what qubits are and how many do we need and where are we today?
Yeah, so quantum networking is fundamentally different from classical networking. So in the classical world, you would think of, let's say Alice wants to talk to Bob, literally, they'll make a packet out of the zeros and ones, and this packet will journey through the switches and eventually reach Bob, right? So, and quantum networking, on the other hand, is completely different. So quantum information transfer happens via a couple of key principles. One is called entanglement. The other one is teleportation. Quantum entanglement is all about generating a pair of photons that basically share entangled states. And think of them as these Amazon boxes, like Alice and Bob have. Okay? And if you want to transfer quantum information from Alice to Bob, literally you put that information in the box that Alice has, and it gets instantaneously teleported to Bob. Now, it may appear like it's actually breaking a bunch of laws of physics here, but it turns out teleportation happens where the information gets transferred, but in order to recover that information, you still need some classical information to go via the classical channel. So as a result, no laws of physics are violated here, but that's the way it works. And what we are really excited about is the entanglement source, which is really what we have actually in the booth right there. So the entanglement source that we have is a small chip that basically generates entangled photons at a very high rate. We have about 200 million entangled photon pairs per second. And the other beautiful feature about this is when you think of quantum, right, you would imagine these gigantic cryo chambers and super low temperatures like close to absolute zero. This chip actually works at room temperature, and it's compatible with existing fiber technology, which makes it super practical and easy to deploy. And so the rate at which we generate these photons is tremendously high, and we will actually increase it substantially further as well. This chip actually is a foundational technology. We need several other components in order to truly enable this quantum network of the future, which are basically prototypes that we're building in our lab, and stay tuned for more updates and in the coming quarters and months.
So one of the problems that we are going after first in the quantum domain, at least the vision, is that we build, again, these distributed quantum computing environments so that you can connect smaller quantum nodes, which are right now 200 qubits. They're really tiny, but you need, for practical computing, you need maybe hundreds of thousands or even a million qubits. So by connecting a bunch of these smaller nodes through this fabric, you can accelerate that timeline for pragmatic quantum computing. So the data center is a restricted enough environment that you can deploy this and experiment with it. And so with that, Bill, coming to you, this is a research prototype, but to make it a reality, what are the challenges that you see from the product perspective to make it real?
Well, first of all, let me say, I think that this is really critical technology, and this team has done a terrific job of advancing the state of this technology. I think Cisco's birthright really is to own networking, and that includes quantum networking. And the idea of starting inside the data center by networking computing elements will give us a lot of insight about what it's going to take to build a larger scale network. So I think this is a really important thing for Cisco, and it's a really important thing for the industry. We're at the research stage here, and many of us have lived in a world where you start in research and you move products into production, early, small scale, and then large scale. And we're early in the life of that, but I think things are moving very quickly. The entanglement source that you see here is a very important first step, and it's generating entangled photons. We need to take this into a production environment, so that means we have to certify a fab that can actually build this thing. As Vijay and Ramana mentioned, we would like this to run at room temperature. If you've seen any quantum computers today, like IBM's quantum computer or Google's, those do not run at room temperature. They require massive cryogenic sources to keep everything cool, very cool. And so we would really like to have technologies that run at room temperature. Another key technology for us inside the data center is the switch itself. The switch has to preserve the quantum state. Today's photonic switches will likely destroy the quantum state. So we have some technology development ahead of us. And then I think the next step is to take this into production environments and climb yield curves, which we're very good at. And we'll figure out how to make this a reliable solution that can be deployed in massive scale for our customers. That's all focused on what's happening inside the data center, which is a good test bed for us to figure out what it's going to take to build larger scale networks.
So this is all great. So you're telling me that it's actually closer than what the research guys are thinking about.
Okay, here we go. Yes, I think it is closer. I'm more of an optimist.
That's amazing. And so let's challenge you a little further. Right? So inside the data center is great, but what we are truly after as a company is to build out the quantum internet. Right. And so there are two parts to that statement. One is, can we connect quantum data centers together to enable long-distance computing? But what is also possible today is you have quantum sensors that are being used for weather prediction, better weather prediction, or for biomedical imaging, and so on and so forth. And you need to build out a quantum internet which carries these quantum signals further and further apart. And so what are the challenges to get to the quantum internet, Bill?
Right, so we have many challenges that have to be overcome in order to build what we would consider a WAN network. We will get there. But as an example, distance is one significant issue for sending entangled photons. Today, there's very limited distance that we can send entangled photon pair and have it survive. And so we need to find a way to extend that distance with things like repeaters. Repeaters would have to preserve the quantum state, and things like memory, quantum memories. And so those technologies are under development right now. There are companies that we are working with. There's a very large partner ecosystem that's developing around this technology. Those technologies are under development, and we will see some of them coming out as early as this year. So one issue is increasing the distance. That's a big issue. Another is increasing capacity, but I do want to put that in context. The first DWDM systems that are used in classical networks were 40 gig systems, 40 gig on the fiber.
Cisco Live. The world of solutions will close in 15 minutes.
Oh, don't go
We have
minutes to closing.
40 gig on a fiber were the initial DWDM systems. 10 years later, we had increased that by an order of magnitude, 400 gig. In the next 15 years, we've increased it by over 2 orders of magnitude. We can now demonstrate 64 terabits of capacity on a fiber. And in addition to that, we've really done a great job of shrinking the technology. This is an 800 gig pluggable optic that can transmit a signal 1,000 kilometers. That's not where we're going to start with quantum. Quantum is not going to be at parity with classical networks. But as Vijay said, there are going to be applications like sensing that can take advantage of short distance applications, low bitrate applications, and deliver very significant value. So I think we're going to see applications emerge that sort of match the state of the technology over time. And I fully expect, just like we did in classical networks, we're going to see massive improvements of the technology over time as well.
Thank you. And I think my goal is to get to a point where we can carry that entanglement source in a pocket, just like Bill carries around that transceiver, because that is a metric to achieve, which tells you that we are at scale.
Right.
Otherwise, we aren't. So, but coming to Anthony, I mean, we are all optimists here. I'm not saying you're not an optimist, but I think we are out there to build distributed quantum computing. And one of the things that it'll do is it'll enable practical applications and algorithms to run on quantum compute nodes faster, or earlier, rather. And so one such algorithm that we are all paranoid about is Shor's algorithm, which ensures, or not ensures, but which actually enables you to compromise existing key exchanges that happen between computers. And this is the whole notion of it can be done either today, or you can go after these store now and decrypt later kind of attacks, where you're snooping into traffic, storing them now, and when you have access to these computers, quantum computers, you can actually make all of that conversation plain text. And by building these distributed quantum compute nodes, we are accelerating even that timeline. So as...
Yeah, gee, thanks.
Yes, so help me, please. Because we're building the technology, but you need to secure it. So what do we do?
Yeah, your optimism is the reality of us security folks, which is it creates a set of challenges that we've got to start to think about now. You did a great job of describing it. I mean, the key risk that we think about that we need to begin to deal with today is the idea that you can capture traffic. And when a quantum computer is created of sufficient scale, which we are looking to enable, that traffic is potentially then decryptable by an adversary. And you know, when you think about that conversation, many people think about that as a big government conversation. I think that's a really relevant set of actors in this space. But you think about the importance of AI and how important data is to AI and will be in the future. There's actually new reasons to want to do this for folks that may not be able to get their hands on all the data that they may want. They may want to choose a way to get after it. So when we think about that classical problem, we've really been engaged today in standards work to help build quantum-resistant cryptographic algorithms. That body of work is something that Cisco's directly contributed to. We worked with NIST and other organizations to create those algorithms and make sure that they're out in the public domain. We're working constantly with standards organizations, in particular the IETF, to get those algorithms leveraged in protocols that we use today. And ultimately, thinking about the risk that we all need to be dealing with today, it is this encryption of data in transit and doing that encryption with quantum-resistant algorithms. Cisco has a robust roadmap across our portfolio that we continue to enhance and refine, which will allow us to implement quantum-resistant cryptographic algorithms. In fact, the campus and branch launch that we've done, that hardware is enabled for quantum-resistant algorithms. This is really essential for us to start to think about now. When I poll my peers and other security leaders in other organizations, to be really candid with you, most of them don't even have this on their radar as things that they're worried about. I tend to joke, maybe they all think that they're going to retire before they actually have to deal with this. But when we think about ourselves as stewards of where we need to be going and what we need to be doing as networking professionals, as security professionals, facing this reality today is super important. It doesn't end there. It's not just about the transport algorithms and how we send information across networks. When quantum computers are created, all of the things that we think about, how, you think about signing an image. So how do you know that it is a legitimate Cisco image? That uses public key cryptography. That in and of itself will be in jeopardy of being compromised. So somebody could create something that looks like a Cisco image, but isn't. There's risk up and down the stack of everywhere that you worry and use cryptography to protect security. We've got to be embracing the future state of where we need to be quantum-resistant algorithms in this space. We're really leaning into it heavily and have invested a lot. We also have a lot of ways that we can enable quantum key distribution inside of our products with standard protocols like SCIP. So this is a rich area that is going to drive what needs to be a fundamental priority for so many of our organizations. And to be honest with you, most of us are just now getting up to speed of this is what we need to be going to deploy. But this is a do it today, especially with this audience of 70, 30 and those timeframes. You've got to be taking these things really seriously today.
So when I think about the timelines and the phased approach here, I mean, there's education, there's visibility as to which services are probably most critical.
Yeah.
You talked about encryption for software at rest or data at rest, but also in transit.
Yeah.
So how would you draw up that timeline, and what should people do to prepare?
Yeah, you've got to take a risk-based approach. You can't fix it all at once. Focusing and getting an assessment done of what your most vulnerable communications are, and taking that assessment and using that to inform your roadmap is a really essential set of things. And Cisco has a set of services that allow for customers to go through that assessment today with our CX organization to understand where is the most risk and how is it that you would address it. It's most likely going to be in your transport layer, and it's most likely going to be in environments where you're traversing on someone else's infrastructure. But we have assessments that can help our customers do that. And in fact, we've done that inside of our own enterprise, which is my job of making sure that we're prepared for this.
So Anthony talked about security and what we can do with standards like the ones that NIST came out with, the post-quantum cryptography standards, which are all software-based. But Ramana, I know that there are other use cases that we have for the quantum network itself. So even though we are building out the quantum network to enable distributed quantum computing, there are a whole set of use cases that are possible today in the classical world. And security is one of them. Can you just talk about a few of the others?
Oh yeah, so in our journey of actually building a quantum network, right? So we started off with this, let's build a quantum network for enabling practical quantum computing, right? Scalable quantum computing. But in our journey, what we found is that there are several practical quantum networking use cases that will actually, quantum networking, that can actually solve classical applications. And that's actually really exciting because we don't have to wait for, I don't know, depending on your choice, it could be 5 years or 10 years. You don't have to wait for quantum computing to be real in order to realize the value of a quantum network. Some of these use cases are, decision coordination. So decision coordination is around, how do you have Alice and Bob, right, take a coordinated decision? It could be stock trading, it could be something else, right? If Alice makes a decision to buy a piece of stock, right, Bob should also be doing it at the same time. How do you coordinate that? In the classical world, you'll actually have to send a message saying, hey, I'm actually taking a decision to sell the trade or sell the stock, and then information would go to Bob, right? If you have a quantum network, turns out you can leverage the entanglement property that I was mentioning before to allow for Alice and Bob to take the same decision at the same time. And that's fantastically interesting application, right? Similar other applications, we have secure position verification, ultra precise time synchronization. So these are all use cases that can actually take advantage of a practical entanglement-based quantum network. Now the fourth one that is listed here is eavesdropper-proof security. So I'm sure you must have heard of the word quantum key distribution, which is leveraging quantum properties to exchange keys between Alice and Bob, right? So that requires a separate quantum network or a dedicated fiber to exchange your quantum keys. But if you have eavesdropper-proof security built out of a quantum network, essentially that means that you can leverage the no cloning theorem property of a quantum channel to detect an eavesdropper, right? You don't have to exchange keys. You just detect that there's an eavesdropper on the wire, and that will allow you to make sure that either you exchange your information or not, depending on what you want to do, right? So these are the kinds of use cases that we can build with an entanglement-based quantum network today. And we don't have to wait for the whole quantum computing revolution to really take place. That's really super exciting for us.
So what you're saying is that even for the optimists in the group, which are saying 5 years out, you're becoming an even more exponential optimist.
Right.
Saying, let's start using the quantum network for classical use cases today because it's here and now. So I already got your answer, so I'm going to move on to Bill. But the question I had was like, what is the one quantum opportunity that excites you today?
Certainly, security is a very clear opportunity, but I think sensing is one application that is just magnificent in terms of the scope of what can be done with quantum networks for very, very, very precise sensing in solving problems that we just can't solve with classical computers.
Anthony, how about you?
Well, for me, the idea that we could not just protect information as it's being transmitted, but detect when someone is listening or potentially trying to listen, that eavesdropper-proof piece of this for me is if you look, there's a lot of people that spend a lot of time trying to figure out whether or not their communications are potentially compromised. And so this for me is, I think, a real game changer in a lot of ways. That classical computing application of this is something that before we started having these discussions, I didn't even realize was a real possibility.
So I think that is the most paranoia-inducing use case that we can all line up behind. But the other thing, I was talking to somebody, and the decision coordination part of it, it's almost like, let's say there was a starting gun that could be heard by anybody across planet Earth at the same time. What could you do with it? And the use case that was brought up was like, hey, I want to play a game with my friend in Tokyo, and I don't want him to get an advantage on the gaming exercise before I start playing the game. Like, he could be starting out first and get an advantage just because he's 3 milliseconds or few seconds ahead of me. So can we have a starting gun which says, start your game now? I said, that's an amazing use case, but boy, you don't want to build out a quantum network just to start gaming, but maybe we do.
You might be surprised.
Maybe at some point, when Bill scales it out, it's cheap enough that we can do that. But with that, I would like to wrap up and say, as we heard today, I mean, yes, the vision is to build out quantum networking and quantum security from the ground up. So it's not just that quantum entanglement source that you can just see behind you, and you can go and visit that booth. But it's also the protocols, the software controllers, the compilers. In the end, you should be able to drop in a few lines in your Python code, and stuff should work. And that's why we want to get towards. But as we do that, we have use cases in the classical world today that we are super excited about. But even above all of that is the paranoia and the realistic check that Anthony brings to the table. Start preparing for it's called the Q day, I think, or a P day. I think there's a term for this. I should know this, where quantum computers would be strong enough that they can break key distribution today, and start preparing for that, because that's a long.
It's called my retirement day.
That's your retirement day.
Yeah.
Hoping all of us are retired by then, but thank you for coming, and if you have questions, we'll be around. Thank you.